what is basically the theory of relativity or the special theory that was given by Einstein. And not only that, what is there any linkage between the string theory and the theory of relativity for that matter? So,
Okay, what is special theory of relativity?
right.
So, we talked earlier about Maxwell's equations and how light is an electromagnetic wave. Out of these equations, when we realized it's a wave, something else came out and was the speed of the wave. So that was one of the few things that made people sure, like, oh, light, it has to be an electromagnetic wave, because it came out that the speed of this electromagnetic wave is 3 times 10 to the 8 meters per second, which is what we have measured. But then that brought a lot of questions, because we were not working with any frame in these equations. And that's fancy talk for what is this speed relative to? Because when I say, like, oh, that's going 20 miles an hour, it's like, oh, with respect to the Earth, or that satellite is going 40 miles an hour, oh, with respect to the International Space Station, or whatever. There's no pure speed or velocity. But this equation was giving us the speed, and people are like, okay, well, what is that in respect to? What is that relative to? It makes no sense that we're not working with respect to anything else in these equations, and a velocity comes out. And this was when people started thinking, okay, maybe the speed of light is a constant no matter who's looking at it. And this was proven experimentally. There's an experiment called the Michelson and Morley experiment where they showed this. But it is not for sure Einstein was inspired by this experiment or not. It could have been just the Maxwell's equations results. So what Einstein said, okay, let's assume, one, that the speed of light is constant no matter who's looking at it. So no matter if you're moving fast with respect to your friend, you're both going to see the same speed. Like if you have a particle of light and you both measure it, you're both going to see the same thing.
Right.
The other thing that he assumed is all observers, or all people that are measuring, can agree on events that happen. Like if I go ahead and high five Arian, then Shrey will agree, yes, they high five. There can't be like, oh no, I didn't see you guys high five. We all agree on reality.
Right.
Okay, so now let me ask you a question. Let's say I'm in my car and I have 2 mirrors. Like I'm just hanging out with some mirrors, and I put a flashlight in between the mirrors and I get some light bouncing between them.
Right.
In theory, this wouldn't work, or in practice, this wouldn't work because, light would escape, whatever. But let's imagine you just have a particle of light bouncing between the mirrors. Now, I'm in my car, moving with respect to you guys. You guys are watching from the sidewalk. From my perspective, this light is just going up and down. But from your perspective, it's going diagonally.
Right.
Okay? Now, this, if we take into account the last 2 postulates that we say, this would lead to some paradoxes if we don't change how we look at the world. So, for example, let's say that for the sake of simplicity, the speed of light is 1 meter per second, because it can be anything, right? Right now we say it's 3 times 10 to the 18th, but that's just a number. It doesn't change anything. Let's say it's 1. And I have my mirrors separated by 1 meter. To me, it takes 1 second for the light to reach between the bottom mirror and the second one. Now for you guys, it's going diagonally, and there's 1 meter between them. So through Pythagoras' theorem, that diagonal is going to be longer.
Distance increases. Yeah.
So it's going to be a little bit more time for you guys. So how does that make sense? When we go back and talk to each other, we have to agree on our reality. right? That's the second postulate. So what happened? Did 1 second pass, or then a little bit over one pass? So how do we fill that hole for the second postulate that we have to agree on reality? That's where Einstein said time is relative. It happened different for you in the car, and it happened different for the people on the sidewalk. And that is the basis of it. That was his thought experiment that started everything. Then it's just working through the math, and you find that not only time, that's called time dilation, where time goes slower, but also there's something called length contraction.
Right.
Which means that distances in space are shortened. And that is the basis of special relativity, that time and space depend on who is asking. If I say I have a meter here, that's for me. That meter might be different for someone else. It might not be a meter between my hands. Depends who's asking.
Right.
But how could be a meter different? 1 meter would remain 1 meter for every person living on this planet.
No. So here's the thing. If I hold my hands 1 meter apart,
okay,
and you go walking by me, to you that's not going to be a meter. It's going to be 0.999999. It's going to be really small length contraction because you can't run that fast. But if you were going almost at the speed of light, that would look really small to you. If you looked at me, it might look, well, I might look like all shrunk up, and my hands would look like they're together.
Yeah. Phenomena. It's kind of a paradox, but it's not quite sure. Everyone is not quite sure about that. I think it's a paradox.
It's not a paradox because it all has solutions. Like you can calculate what would space be for everyone. There's something important. When I said like, oh, you would see me like this, it's not only that you would see me shorter. Like, oh, you're not really, your hands are not really 1 meter or less than a meter apart. I just see you that way. No, to you, they're actually less than a meter apart. They are a shorter distance. It's not that you see it. It's that space depends on who's measuring it, on the frame of reference.
I think this was...
Please continue. No, go ahead.
No, I was just saying that when Einstein I think observed the clock tower when he was moving through bus. I think that was his eureka moment when he realized that the speed of our hand is different when he's moving fast with respect to others.
Yeah, I think that's right.
So is there a difference between the theory of relativity and special theory of relativity?
Yeah, so...
Or are they same?
Einstein came out with this, he published this special theory of relativity because this is a special case. The general theory of relativity is a complete picture because in special relativity, you don't take into account accelerations. It doesn't take into account, it just says, oh, if I'm moving at 20 miles per hour with respect to you, this is what you will see. But it doesn't say what will happen if I'm accelerating at 20 miles per hour. You cannot solve that with special relativity. And Einstein had another eureka moment, what he calls his happiest thought ever in his life, when he realized that acceleration and gravity are the same thing.
Right.
The equivalence principle. Like, I'm in my room and I don't know, there's no way for me to know, there's no experiment I can do inside my room to know if my room is accelerating upward, like I have a rocket on my room, or if I'm just being pulled by gravity down. They're the same thing under the laws of physics. So he developed the theory for that, and that way you can take into account accelerations, which is gravity. So special theory of relativity works when there's no gravity. It's when space-time is flat, which is one case out of the general theory of relativity. The general theory of relativity works for any space-time, including the flat. So from general theory of relativity, you can derive special theory of relativity.
Okay. And how is acceleration equal to gravity? I didn't get that.
Okay. So let's say, imagine you're in a dark box. You can't see anything. And you're maybe floating in space. So you're in this box and you're floating, you're in your astronaut suit, and then suddenly you feel like the box comes up from below you and starts pushing you up. So now you can stand on the box. You're standing on it,
Right.
and you're like, whoa, what's happening? Tell me a way. You can bring anything you want. Is there anything you can do from inside the box without looking outside to know if the box is being pushed up by some rocket, like it's accelerating, or if maybe you're near a planet now and there's gravity pulling you down? There's no way. They are physically the same interaction. They're the same thing. This is what Einstein showed, that gravity is just the same thing as acceleration. And in fact, under the theory of relativity, there's no force of gravity. There's nothing pulling you down. This is going to sound really weird.
Right.
But, and I don't fully understand it either, because when you do your undergraduate degree, I took a class in general relativity, but they don't go into much depth. People usually study that in graduate school. In theory, you're not being pulled down. The floor that you're standing on, that I'm standing on, is accelerating.
Pushing upwards. Okay.
Or you are attracting one in each other through invisible force.
If that were true, if I went under the floor, I would be pulled up, which does not happen.
But gravitation force is the attractive force, right? So you will be attracted towards Earth, not be repelled by it.
Yeah, so that's the Newtonian, that's Newton's theory, that there's an attraction between things, there's a force.
Some truth to it.
There is some truth, but that is a simplification. The theory is so much more complicated. It says that space and time curves, and you're just following that curve in space-time. And right now, I'm trying to follow that curve, which goes into the center of Earth, but this floor is stopping me because the floor is accelerating upwards. It's really complicated, but there is one experiment that is proposed to prove this. Through Maxwell's equations, we know that if we move a charge, like let's say you have an electron has an electric charge. If you move it, every time it accelerates, it has to emit radiation, so light. If you have a photon moving in a straight line and you push it, it emits radiation on the other way. Accelerating, you don't have to understand why, but accelerating electrical charges, they emit light, okay? That is a property of electric charges. Now, if Einstein's theory of relativity is true, then if you had an electron lying on your table, and it's true that the table is accelerating upwards, then it should be constantly emitting radiation, even if it's just sitting on your table.
But the pressure isn't much.
What's that?
But the pressure is not that much that the electron will emit radiation.
The pressure? What pressure?
The pressure from the table, because table is also stable. If it's going upward, we can't feel it.
So it's a thing, you can't feel it. Like if you stand on the table, it's holding you, right? And why is that holding you? That's the thing, because Einstein's theory of relativity says that the table is accelerating. It's stopping you from moving.
Pressure that is being exerted by the atoms that are inside any object.
Yes.
Roughly, they are emitting some pressure, that you want to say. The electrons are emitting pressure away from the gravitational force.
Yes.
So they are not exhibiting the property of gravitational force. It's different from that.
The difference is, like, if you imagine the table in space and you just put the electron on it, then they might be touching, but it's just there. But if you start accelerating that table up, that electron should start giving off photons, light particles, because it's being accelerated.
Okay.
So the thing is to make that experiment on Earth. If Newton's right, then the electron is not being accelerated because it's on the table, it's not moving, it's at rest. If Einstein's right, then that electron you will have it not moving on your table, and then you will see it radiating light.
Right.
Okay.
So that is a way to show once more, because we have already shown that general relativity is true through other experiments, but that will be another one. But it's really hard to do because, well, what was the issue? I asked my professor this. It's really hard to see because gravity is so weak, it's hard to see it acting on electric charges. We would need really, really high precision.